Hi, I'm Marc Roth, and this is Mathematics for Social Justice. Today we'll be finishing up quadratic equations, which we began in the previous video, and then we'll be taking a look at Pythagorean triangles. So we're going to continue with the lesson of a previous video using an old Babylonian method. So a problem that was actually done in ancient Mesopotamia, modern-day Iraq, was to start with a rectangle and try to find its length and its width if you're given its area and you're given the difference of its length and its width. So let's draw a rectangle. And we're going to compare it to a square with the same perimeter. So if the square is m by m, its area is m squared. And here we want the length to be 7 more than the width. So we'll break 7 in half, and we'll have m plus 3.5 compared to m minus 3.5. And that'll make the area m squared minus, now I have to multiply 3.5 times 3.5, and I have a trick. Okay, so when I'm timesing two numbers and the temps and this column has the same digit twice, and these two digits add to 10, I can cross this out and make it one more. And 3 times 4 is 12, and 5 times 5 is 25. Now the area of the rectangle is 60. Now, it turns out that the square will have the area 60 at plus 12.25, which makes the area of the square 72.25. And if I am, I can use the trick again, but I have to use it backwards. So I can see that it's going to be 8.5 times 8.5. Because then I can cross this out and make it one more. 8 times 9 is 72. And 5 times 5 is 25. I now know that the area, a square of this area has a bottom of 8.5 and a side of 8.5. And so m is 8.5. 8.5 plus 3.5 is 12. And 8.5 minus 3.5 is 5. So now I found the dimensions of the rectangle. So now we're going to use the old Babylonian method to derive the quadratic formula. So if we have ax squared plus bx plus c equals 0, I can divide both sides of the equation by a. The a's cancel in x squared plus b over ax plus c over a equals 0. Now I can subtract c over a from both sides. This cancels, and I get x squared plus b over ax equals negative c over a. Now I can factor out an x and get x times x plus b over a equals negative c over a. The next thing I'm going to do is multiply both sides of the equation by negative 1. Now when I multiply the left side by negative 1, I have to choose to either multiply this term or this other term by negative 1. I'm going to choose this larger term. So it's going to be x times negative x minus b over a equals positive c over a, because I'm also timesing by negative 1 on the right. So now we're going to draw our square and a rectangle of the same perimeter. And label this m, and m squared. Label this m minus d, m plus d, m squared minus d squared. and the area is C over A. And this will be our two sides of a rectangle. I can choose to put the x here or here, but I'll put it here. And the other side is negative x minus b over a. Now, again, these two have the same perimeter, so they have the same semi-perimeter. This plus this is equal to this plus this. So the x and the negative x cancel when I add the two sides. And I get negative b over a. So when I add these two sides, I also get negative b over a. So this is negative b over 2a. And this is also. And the area is going to be b squared over 4a squared. I also use my piece of the number line and put m in the middle. And this is d and d. And this is m minus d, which is one of our unknowns. And this is m plus d, our other unknown. And m now is negative b over 2a. So we're thinking of d as being the side of a little square. And the little square has the extra area that's in the square and that is not in the rectangle. So this is d squared. Okay, so d is equal to the square root of what's in here minus what's in here. So at this point, we need a common denominator. We times the denominator and the numerator by 4a. So that's equal to the square root of b squared minus 4ac over 4a squared. And that's equal to the square root of b squared minus 4ac. And the square root of this I can do in my head. That's equal to 2a. So I now know d. Square root of b squared minus 4ac all over 2a. And same thing here. So if I add these two guys, I get one answer. If I do this minus this, I get the other answer. Okay, so our final result is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So now I'd like to consider another problem that was worked on by the ancient Babylonians, and that's Pythagorean triangles, where you have right triangles where all three sides are whole numbers. So one, for example, would be the famous 3, 4, 5 right triangle. Where this is a right angle. Well, suppose we didn't know this leg and this hypotenuse. We only knew this leg. How would we determine the other two sides? So let's start with this picture and draw the squares adjoining each side. So again, this is 3. So this is also 3. So this is 9. We don't know this side yet, so let's call it D. And this side we'll call M. So these two will be M squared and D squared. And according to the Pythagorean theorem, M squared minus D squared equals 3 squared. So M squared minus D squared equals 9. And we can factor M squared minus D squared. So it's equal to M plus D times M minus D equals 9. And I can use my visual aid. So this will be M, this will be M minus D, M plus D, and this distance is D. And I want M plus D times M minus D to be equal to 9. And I want to use whole numbers. So I can only go 1 times 9. I can't go 3 times 3 because they're two different numbers. So M is going to be halfway in between. So I can add the two ends and divide by 2, and I get 5. And D is 4. So that gives me 4 and a 5. And I end up with the famous 3, 4, 5 right triangle. Okay, so we're going to do another example, but we don't have to draw this ornate picture. Suppose we have a triangle and its leg is 5. So all we have to do is draw the number line and try to have this number times this number equal 5 squared. Not 5, but 5 squared. So 5 squared is 25, so we want this number times this number to both be whole numbers and both odd or both even, and we want to make 25. So 1 times 25 is our only choice, and the number in the middle is 1 plus 25 divided by 2. So 26 divided by 2 is 13, and 13 minus 1 is 12. So this gives us the hypotenuse and the other leg. And again, this is a right triangle. So we found a Pythagorean triangle very quickly using this visual aid. Let's do one more example. So suppose we're looking for a triangle that has a leg of 7. So we square 7 and get 49. So we want this times this to equal 49. So again, it's 1 and 49. So in the middle, it's going to be 1 plus 49 divided by 2, which is 25. 25 minus 1 is 24. So these are the other two legs, other two sides. We have a leg of 24 and a hypotenuse of 25. Okay, so now let's look at an example where there's more than one answer. Suppose we want a leg of 12. There's several different Pythagorean triangles that have a leg of 12. So to find them, we need to find all the two-factor factorizations of the square of 12. So we want to find all the ways to write 144 as the product of two numbers. But not any two numbers. They have to both be even or both be odd. Well, they can't both be odd, but in this case, they have to both be even. And so to do that, we can use another visual aid. We're going to start by making a factor tree. So you take 144, and you can separate it. It doesn't matter how you start. We're going to end up with the same prime factorization, but we're going to start with 12 times 12, and then go 3 times 4. Again, 3 times 4. And then 4 is 2 times 2. And we circle all the prime numbers. So our prime factorization of 144 is 2 to the 4th power times 3 to the 2nd power. Now we can draw that with a rectangle. And since this number is 4, we're going to have 4 vertical lines. And this other exponent is 2, so we're going to have 2 horizontal lines. And we're going to use these numbers to find factors. So we have 4 2's available. If we use all 4 2's, that's 16. If we only use 3 of the 2's, that's 8. If we only use 2 of the 2's, that's 4. We can use 1 2. And if we use no 2, it's 1. It's not 0, it's 1. Again, we have 2 3's available to make factors. We can use both 3's, which is 9. Use 1 3 only, or don't use a 3 at all. Now we fill this in like a times table chart. So 1, 2, 4, 8, 16, 3, 6, 12, 24, 48, and go 9, 18, 36, 72, and 144. We'd like to find the two-factor factorizations of 144. To do that, we can think of a point in the center of this center square, and we're going to rotate 180 degrees. When we do that, 1 and 144 equal 144. And if we times 2 times 72, we also get 144. So again, when we do the 180-degree rotation, 2 and 72 trade places. And then 4 times 36. And then 8 times 18. Sixteen times 9. 3 times 48. 6 times 24. And 12 times itself. So now we can eliminate some of these. We don't want 12 times 12 because we don't want the same number twice. We also don't want an odd and an even factor because then the center won't be a whole number. So we're going to eliminate that one, and this one, and this one. So we only have four possibilities. Actually, they're all good. Each one of these will give us a Pythagorean triangle that has a leg of 12. So for example, if we start with 2 times 72, if we draw 2 and 72, to find the middle, you're going to add and then divide by 2. So 74 divided by 2 is 37, and 37 minus 2 is 35. And we end up with the other two sides of the triangle. So this would be 35, 37. Okay. So what about changing to 4 times 36? So this time the center will be 20. Minus 4 is 16. So we end up with 12, 16, and 20. So what about 8 and 18? If we have 8 and 18, the sum is 26. Half of that is 13. And 13 minus 8 is 5. So we end up with 5, 12, and 13. And last but not least, if we use 6 and 24. The middle will be 15, and the difference will be 9. So I end up with 9, 12, and 15. So we were able to use a similar visual aid that we use with quadratic equations and also use it with Pythagorean triangles. Both problems were solved by the Babylonians. So many students need computational practice. So when we're working with fractions, we often give students, one-step problems or two-step problems. But how about trying multi-step problems? Well, we can do that with Pythagorean triangles. So for example, if I go 1 minus a fraction squared on top of 1 plus the same fraction squared, I'm going to end up with a Pythagorean triangle. So for example, suppose I put 2/3 here and 2/3 here. So now I can solve this, and when I finish, I'm going to get a fraction, and the numerator is going to be the leg, and the denominator is going to be the hypotenuse of a Pythagorean triangle. So I think this is a valuable exercise for students who need to practice computation. So this would become 1 minus 2/3 squared, which means we're timesing 2/3 by itself, and 1 plus 2/3 times 2/3. So now this step was very easy. We're just saying 2/3 squared is 2/3 times 2/3. The next step, slightly harder. We multiply the two numerators, we multiply the two denominators, and we get 1 minus 4/9 over 1 plus 4/9. And then we can change one whole into many things, like 2/2, 3/3, but it's easiest to change it to 9/9. So we get a common denominator. So then, when we subtract, we keep the same denominator. So I can think of this as a pizza problem, where I have a pizza with 9 slices of equal size, and I have 9 slices, and I subtract 4 slices, and I still have 5 slices. The denominator doesn't change because I haven't changed the size of my slice, just how many slices I have. And down here, I have 9 slices plus 4 slices gives me 13 slices of the same size. So the denominator again doesn't change. Now I can use what's called the golden rule of fractions. I can times the top and the bottom by the same number. So in this case, I can times by 9 and by 9 and cancel, and I get the final answer of 5/13. So again, we have a leg and a hypotenuse of a Pythagorean triangle. So 5 is a leg and 13 is the hypotenuse. And I just have to determine the other leg. Well, to do that, I can use the Pythagorean triangle, and the other leg is going to be the square root of the hypotenuse squared minus the leg squared. So it's going to be the square root of 13 squared minus 5 squared, which is equal to 169 minus 25, which is the square root of 144, which equals 12. So this leg is 12. A related problem is to do this problem. 2 we can also get a Pythagorean triangle by using this structure. So let me use the same fraction 2/3. When I go 2 times 2/3, when you think about pizza, I'm timesing by 2. I'm only timesing the number of slices. I'm not changing the size of the slice. So if I want twice as much pizza, 2/3 becomes 4/3. And when I get out of elementary school, I think I'm not going to bother by changing 2 to 2 over 1. I think we can go straight from 2 times 2 to 4 and keep the same denominator. So again, I'm going to go 2/3 times 2/3. And then I'm going to do my simplification. So I get 4/3 over 1 plus 4/9, timesing the two numerators, timesing the two denominators. So that becomes 4/3. Again, I'm going to change this to 9/9, so I get a common denominator. So that's equal to 4/3 over 13/9. And I'll use the golden rule of fractions. I'll times the top and the bottom by the same thing. And I'm going to use the reciprocal of the denominator. And I have to use the same thing above. And I can cancel and cancel. I can also cancel one more time, cancel the 3 and the 9. So divide by 3, divide by 3. 4 times 3 is 12. And 1 times 13 is 13. So again, I get a Pythagorean triangle. Its hypotenuse is 13, its leg is 12. And so before we ended up with 5 12ths, now we end up, 5 13ths. Now we end up with 12 13ths. So we're going to use Pythagorean triangles now to learn some easy algebra. So if we pick a point, let's say this is 2/3 of the way up, this will be the point 0 2/3. Now if I draw this segment and I intersect the semicircle of the unit circle, this is actually the unit semicircle, and if I also draw this segment, it's well known from geometry that this angle will be a right angle. So a triangle inscribed in a semicircle is a right triangle. I believe this is called Thales's theorem. And we also know from algebra that when two lines are perpendicular, their slopes have a relationship. One is the negative reciprocal of the other. Now, what's the slope of this line? Well, we're rising 2/3 and we're running 1. So it's 2/3 over 1, which is just 2/3. So if we write y equals mx plus b, which is the slope-intercept form for the equation of a line, m again is 2/3. And the y-intercept is where the line crosses the y-axis. It also crosses at 2/3 because this is the point 0 2/3. So we end up with the equation of line y equals 2/3 x plus 2/3. So what does that mean? That means if you think of a function as an input-output thing, we have an input x going into the function machine. 2/3 of x plus 2/3 comes out. So whatever goes in gets multiplied by 2/3, and then 2/3 gets added. Pictorially, if this little distance is your input, this distance is your output. Now, the other line, its equation is going to be related because this slope and this slope are related by one's the negative reciprocal of the other. So this second equation will have, I have to flip this upside down and change it from positive to negative. Now I have to think a little bit because I can't see where this line's going to go up and hit the y-axis. So instead I have to think. I know what its slope is going to be. I know its slope is -3/2. So it has to drop 3/2 before it runs 1 hole. So rise is going to be -3/2, run's going to be 1 hole. So that means I have to drop from 3/2 so that my rise is a -3/2. So this y-intercept will be 3/2. Now, for this other line, same thing. If this distance is my input, this vertical distance is my output. If I were to have this equal to this, and I solve for x, it would tell me the point where the same input gives you the same output for both of these lines. So all I have to do is write this equation and solve for x to know this distance. Well, that's related to Pythagorean triangles, because if I drop this line, drop this perpendicular, and connect these 2 points, I'm going to get a right triangle. And it's going to have rational sides. So I'm going to be getting this right triangle, which I can convert later to a Pythagorean triangle with whole number sides. So I just have to do this algebra. So I have to solve 2/3 x plus 2/3 equals -3/2 x plus 3/2. Okay, so what I can do now is put each term in its own parenthesis with a little space in between. So I have 2/3 x in its own parenthesis plus a little space, and then 2/3 in its own parenthesis equals -3/2 x in its own parenthesis plus 3/2 in its own parenthesis. So now I want to times by the same number in front of each parenthesis, and I want the least common multiple of the denominators. So the least common multiple of 3, I can write that like this: LCM of 2 and 3 is equal to 6. So I want it times by 6, 6, 6, and 6. Now I can simplify by canceling. Okay, I can cancel the 3 and the 6, divide by 3, divide by 3. Divide by 3, I get 1. Divide by 3, I get 2. And I am careful to write the 2 above and not below. And I can keep canceling like that. Ending up with 2 times 2x, which is 4x, equals 4. Plus 4, excuse me, equals -9x plus 9. So I need more space, so I'm going to erase this, write this higher. Okay, so I have 4x plus 4 equal -9x plus 9. And now I want to get all my x terms on the left and all my non-x terms or constant terms on the right. And when I'm talking about the left and the right, I'm talking about the left side and the right side of the equal sign. So I can subtract 4 from both sides. Therefore, I can cancel. And I can add 9x to both sides. So I can cancel. And I end up with 13x equals 5. And divide both sides by 13. I get x equals 5/13. So that means this distance here is 5/13. So, and this side is 1 because it's a unit circle. So all the radii have a length of 1. So I now have a right triangle where this is 5/13 and this is 1. Now, what I'm going to do now is blow this up by timesing every side by 13. So this becomes, so if I times by 13, I get 5, and I get 13. And to get the other side, I can simply use the Pythagorean theorem and go the square root of 13 squared minus 5 squared, which is the square root of 169 minus 25. I get the square root of 144, which is equal to 12. So I end up with a Pythagorean triangle. So I can use Pythagorean triangles to teach fractions. I can also use Pythagorean triangles to teach algebra and a little bit of analytic geometry. So next what we're going to try to do is replace the numbers with letters to see if we can derive a formula for Pythagorean triangles. So we'll let this point, instead of being 0 2/3 like it was last time, we'll let it just be d over m instead of 2 over 3. So we're going to start with the formula again. D over m x plus d over m, which is the equation of this line. Well, it's the output of this function of this line. So that's going to be equal to the negative reciprocal of d over m, which is negative m over d, x plus m over d. So again, we can multiply both sides by the least common multiple of m and d, which is going to be md. So we're going to take each term, put it in its own parenthesis, leaving space in front of each parenthesis. And timesing by md. Each term is being multiplied by md. So the m's will cancel, the m's will cancel, the d's will cancel, and the d's will cancel. So we end up with d squared x plus d squared equals negative m squared x plus m squared. So we'll give ourselves some more room. So d squared x plus d squared equals negative m squared x plus m squared. So this is not an x term. We want to get rid of it from the left side of the equal sign. So we subtract d squared. And we have to do it to both sides. And we don't want an x term on the right side of the equal sign. So we cancel that. We add m squared x. We do that to both sides. So this and this cancel. So we get m squared x plus d squared x equals m squared minus d squared. And we finally finish by dividing both sides by well, we can factor out an x. So we get m squared plus d squared times x equals m squared minus d squared. And when we finally do the last step, we're going to end up that x is equal to m squared minus d squared over m squared plus d squared. So we end up with a right triangle where we have a hypotenuse of m squared plus d squared and a leg of m squared minus d squared. Now, we still want to find the other leg. So we can use the Pythagorean theorem, or we can do it a different way. Okay, we've already calculated that if we have a right triangle inside a unit semicircle, that this length will be 1, and this length will be m squared minus d squared over m squared plus d squared, where d over m is the slope of this line. And negative m over d is the slope of this perpendicular line. So now we want to find this length. To do that, we could use the Pythagorean theorem, but another possibility is to use something called the harmonic mean. And the harmonic mean has a formula that's equal to 2ab over a plus b. This height will be related to this height and this height. It'll actually be half the harmonic mean of this distance and this distance. So we need to find this distance. So since the slope of this line is d over m, when we go 1 unit, this length is, this rise is d over m. And when we go this distance, the next rise is also d over m. So this height here is 2 times d over m. Now this slope is negative m over d. So when we're going the other direction, right to left, it's rising m over d, and then rising m over d again when we go a unit and a unit. So this is going to be, this distance here is going to be 2 m over d. And there's a theorem, which isn't too hard to prove, that if you have a post sticking straight out of the ground and a second post sticking straight out of the ground, and you run a wire tautly from the top of one post to the bottom of the other, and vice versa, that the crossing height, the height of where they cross, is equal to half the harmonic mean. So in other words, it's equal to half of this, which means we take away the 2. So if we just find the product of the 2 lengths and divide by the sum of the 2 lengths, this will give us this height. So we want to find that was d over m. We want to find the product, 2 times d over m times 2 times m over d. That's their product divided by their sum. Now I'm going to do a little canceling. I can cancel my m's, cancel my d's, and I can actually cancel one of these 2's with these 2 2's. So in other words, I can factor out a 2 here. And cancel. So I end up with 2 over d over m plus m over d. Transferring from this side to this side, I have 2 over d over m plus m over d. And at this point, I can add these 2 fractions by using a method I sometimes call the zip, zip, zip method when I'm teaching my students. So I'm going to go zip, zip, zip. So each zip is multiplication. So I go d times d, m times m, and m times d. And all that's over 2. And then I can times the top and the bottom by md. So this cancels, and I end up with this height, it's equal to 2md over m squared plus d squared. So at this point, we can move this into a separate picture, and we have one hole, and we have 2md over m squared plus d squared, and we have m squared minus d squared over m squared plus d squared. Now I can blow this up by timesing all three sides by this denominator. And when I do that, I get m squared plus d squared and I get m squared minus d squared, and I get 2md. Now, what happens is, this is a famous formula that was discovered by the ancient Greeks, if not earlier, and it turns out if we start plugging in numbers, we're going to get repeated solutions. And the reason for that is we could actually take this particular triangle and flip it. So instead of having, you could flip it into a different orientation. So you could actually flip this and get the same triangle in a different orientation. So if you don't want to get duplicate answers, all you have to do is worry about the parity of m and d. So if you let one of them be even and one of them be odd, so in other words, your fraction d over m, we can use fractions like 1 over 2, where you have an odd and an even. But we won't use a fraction like 1 over 3, because it turns out using 1 over 3 will give you the same triangle as 1 over 2. So we'll be using things like 1 over 2, one's even, one's odd, one's even, or 2 over 3, opposite parity, or 3 over 4. And we can, and again, if this is in lowest terms, we're going to be getting different Pythagorean triangles. So again, let me use 1 over 2. So if I go m squared minus d squared and 2md and m squared plus d squared, I'm going to get a Pythagorean triangle. So let's let m equal 2 and d equal 1. So again, this is going to be 2 times 2 minus 1 times 1. That's equal to 3. And that's going to be 2 times 2 times 1. That's going to be equal to 4. And that's going to be 2 times 2 plus 1 times 1. That'll be 5. And we get the famous 3, 4, 5 right triangle. So let's do another one. Let's do one where m is 2 and d is 3. I'll actually do it the other way around. M is 3 and d is 2. So it's going to be 3 times 3 minus 2 times 2. That's going to be 9 minus 4, that's 5. And we can go 2 times 3 times 2, which is going to be 12. And that's going to be 3 times 3 plus 2 times 2. It's going to be 13. So we basically found a result of the ancient Greeks where these little formulas give you the sides of a Pythagorean right triangle.